Welcome to this explainer where we're going to completely dissect the mathematical anatomy of medical imaging filters. Today we're doing something truly fascinating. We are going to translate dense academic physics equations into the literal real-world clinical reality of diagnosing patients. We'll see exactly how numbers on a page directly manipulate the pixels that doctors rely on to literally save lives. It's going to be a great journey.
Okay, let's take a really quick look at our roadmap for today. We're covering the physical blur problem, how we translate space to frequencies, the baselines and smoothers, smart restoration, spectrum synthesis, and finally, the resolution seesaw.
All right, starting right off with Section 1, the physical blur problem, or as I like to call it, the biological bottleneck.
So, before we can even think about applying any mathematical filter, we run into a major biological roadblock. Think of it like this. When a gamma photon strikes a thick scintillation crystal, it completely disperses its light into a wide cone before that light even reaches the photomultiplier tube array. Because of this massive spread, the camera has to use what's called Anger logic to calculate the spatial weight and pinpoint the event. But, well, here's the catch. Because of Poisson's statistical fluctuations in that pool of light, there's an inherent physical uncertainty in the calculation itself. Basically, this creates a baseline physical blur before our image is even fully formed.
Moving right along to Section 2, translating space to frequencies, using the Fourier series.
So how do we actually fix that physical uncertainty? Well, we rely on a fairly straightforward three-step workflow. Step 1 is dealing with that physical origin and the quantum uncertainty we literally just talked about. Step 2 is signal construction. This is where we mathematically translate the spatial image into measurable frequencies. And once we finally have everything living in the frequency domain, we arrive at Step 3, frequency modification. This is where the magic happens, and we clean up the spectrum, carefully balancing statistical noise against optimal spatial resolution.
To really grasp how that frequency translation works, we have to look at the Fourier series reconstruction equation. Let's dissect this equation like it's a biological organ. Notice that 2n-1 piece? That tells us we only use odd harmonics. Why? Because symmetric boundaries absolutely require half-wave symmetry, meaning all the even harmonics physically cancel themselves out. But the real clinical translation here is profound. Low frequencies construct the general shape and bulk volume of an organ, while high frequencies are strictly required to build and sharpen the actual edges.
But, nature doesn't just hand us infinite high frequencies to play with. Our real-world equipment, things like physical collimators or digital matrices, forces us to truncate or cut off those infinite frequencies at a finite number, which we call n. And this limitation forces us to confront the Gibbs phenomenon, which is a very strict mathematical limit of reality.
The mathematical limit of this truncation actually guarantees a strict overshoot of exactly 8.95% at any sharp discontinuity. No exceptions. Now, increasing our n makes the ringing narrower, sure, but it never decreases the height of that overshoot. Clinically, this overshoot literally manifests as artificial halos or star artifacts right near high-contrast interfaces, like dense cortical bone or metal implants. And the scary part? These artifacts can actually mask real adjacent pathology from a diagnosing doctor.
Let's dive into Section 3, the baseline and smoothers, and map out our diagnostic taxonomy. This taxonomy operates entirely on a normalized frequency scale, stretching from f equals 0 all the way to f equals 1. Think of f equals 0 as our flat background, sort of the center of the spectrum. Then f equals 1 is our absolute digital limit, which is known as the Nyquist frequency. We group our tools into 3 distinct columns here: the baseline high-pass filters, the low-pass smoothing filters, and finally, the advanced smart restoration filters.
We start with our absolute baseline, the ramp filter. This filter is great because it perfectly removes that simple 1/r blur artifact that we get from basic back projection. It does this by successfully suppressing the low-frequency background hum down at f equals 0 while preserving the sharp edges up at f equals 1. But it has a fatal flaw. By scaling linearly all the way up to the Nyquist limit, it disastrously amplifies high-frequency statistical noise, like Poisson noise from low count rates. It just blows the noise completely out of proportion.
So to solve that fatal flaw, we bring in the Butterworth filter. This is literally our clinical workhorse. Its equation uses a cutoff frequency, set to 0.5 in this specific dataset, which is where the signal power drops by half, also known as the -3 decibel point. It also features an order variable, denoted as n, and this controls exactly how steep this drop-off is. A lower n gives you a nice smooth transition that avoids ringing, but it lets some of that noise slip through. A higher end, on the other hand, creates a sharp brick wall that completely blocks noise, but it introduces severe ringing artifacts right back into our spatial image.
Now let's directly compare two closely related windowing filters, the Hamming and the Hahn. The Hamming is incredibly clever. It leaves a tiny mathematical pedestal of 0.08 right at the boundary. This prevents completely zeroing out those high frequencies, which actually keeps some signal vitality alive. The Hahn filter, on the other hand, zeroes out completely at the extremes. It completely drops its pedestal for slightly better noise suppression, but as a trade-off, this results in much heavier spatial smoothing.
Seeing these curves side by side really hammers the point home. Notice that 0.08 pedestal holding the curve slightly above the baseline on the Hamming side? Contrast that with the incredibly smooth absolute zero taper of the Hahn filter. Both of these are heavily suppressing those upper-end frequencies, but they take slightly different philosophical approaches on whether or not to entirely destroy the high-end signal.
For our final smoothing tool, let's look at the ultimate smoother, the Gaussian filter. It uses a standard deviation to control the frequency spread and a quadratic exponent that decays massively fast. I mean, at just f equals 0.5, the value is already plummeted to 0.044. Because the Fourier transform of a Gaussian is also a Gaussian, this guarantees absolutely zero ringing artifacts. Zero! But the clinical consequence is a massive cost. It heavily blurs the true biological edges.
All right, Section 4, Smart Restoration Filters, focusing on active deconvolution.
What if we want to be a bit smarter than just clumsily chopping off high frequencies? Well, this is where things get really elegant. Meet the Wiener filter. The crucial point of the Wiener filter is that it doesn't just blindly throw away frequencies. Instead, it actively uses the camera's known physics, the MTF or modulation transfer function, paired with a frequency-dependent noise-to-signal pedestal. By calculating exactly where the signal is strong versus exactly where the noise is dominant, it can actually deconvolve or essentially reverse the blur while safely tossing out the garbage data.
And the METS filter takes this smart restoration even further. Starting with a baseline Gaussian blur model, it multiplies it by an inverse boosting operator. Right in those mid-frequencies, like say around f equals 0.2, the boosting term actually goes above 1.0, hitting exactly 1.394. Because it goes above 1.0, it is mathematically amplifying those specific frequencies to recover lost edges that the physical camera blurred away in the first place. It's kind of brilliant.
Moving on to Section 5, Synthesis of the Spectrum, where we look at the master overlay.
I absolutely love looking at this master overlay. It's so satisfying. You see the ramp filter shooting linearly right up into the noise dominance zone? Do you see the Gaussian plummeting immediately because it prioritizes heavy smoothing? You see the Butterworth acting as that perfectly balanced workhorse right in the middle? And the METS filter taking a little detour above the 1.0 line to recover those edges before finally rolling off. This is visual proof that these filters aren't just stronger or weaker than one another. They are fundamentally different mathematical structures actively manipulating the frequency spectrum.
And finally, Section 6, the Resolution Seesaw, exploring the core tension of our field.
This brings us to the ultimate realization of this explainer. Everything we've covered today is really just a massive balancing act on this mathematical seesaw. On one side, you have high-edge resolution, using tools like the ramp or a high-order Butterworth. You get maximum edge detection, sure, but it forces you to tolerate high statistical noise and major ringing risks. On the flip side, you have heavy smoothing, using a Gaussian or a Hahn filter. You get absolute noise suppression, but you're forced to tolerate severe edge loss. The smart balance, using the Wiener, METS, or a low-order Butterworth, lives perfectly at the fulcrum, recovering edges while perfectly managing that mid-range noise.
So, the big takeaway today is clear. There is absolutely no such thing as a perfect filter. There's only the correct mathematical anatomy for the specific clinical task in front of you. Next time you're looking at a complex medical scan, just pause for a second and ask yourself, which side of the mathematical seesaw did the technologist have to prioritize to save this patient's life?